Every heat storage system discussed on this channel has relied on sand. The 2-drum battery, the solar pond, the thermoacoustic generator. In every design, sand served as the thermal medium. Cheap, easy to find, stable under extreme heat, chemically inert. That decision was not incorrect, but it was incomplete. There's another material spread across volcanic regions on every continent that performs better than dry silica sand in ways that matter. It retains heat around 40% longer at identical mass. It survives repeated thermal cycles with greater stability. It does not require drying before use, and in the regions where it naturally exists, the cost is almost negligible, around $8 or less for enough material to fill an entire drum from landscaping yards or garden supply centers. That material is basalt, a dense, dark, fine-grained igneous rock created when lava cools rapidly at the Earth's surface. It forms the ocean floor. It is crushed into road base. It sits in garden centers from Iceland to Hawaii, from Ethiopia to Indonesia, across the Pacific Northwest and beyond. It is abundant, inexpensive, and most people have never been told it can outperform sand as a thermal battery. Basalt carries a specific heat capacity of roughly 840 to 900 joules per kilogram per Kelvin, placing it near sand in that category. But the major difference appears in thermal conductivity. Basalt transfers heat at roughly 2 to 3 times the rate of sand, while also carrying substantially greater density per cubic centimeter. Those combined properties change everything. A drum packed with basalt stores more total energy in the same physical volume than a drum filled with sand. It absorbs heat faster during charging. Then it releases that stored energy more gradually over a longer discharge period. The outcome is straightforward. The system continues operating about 40% longer at the same charging temperature before the heat output falls below useful levels. That number is not marketing language. It comes directly from the material physics. The calculations can be checked before spending a single dollar on construction. Thermal storage using basalt is not some modern discovery. Evidence of the concept exists openly across multiple civilizations. The Finnish sauna is among the clearest examples. A traditional QAS stove uses a large mass of rounded volcanic stone stacked above a wood firebox. The fire burns intensely for 1 to 2 hours. During that period, the rocks absorb combustion heat at temperatures exceeding 500 degrees Celsius. Once the fire fades, the stone mass continues radiating warmth through the sauna for another 3 to 4 hours. Every Finnish household operating a traditional sauna already understands the real principle. The fire itself is not the heating system. The fire only charges the system. The rocks are the battery. Roman bath engineers applied the same idea centuries earlier. The caldarium incorporated thick stone benches and wall sections built from dense volcanic tuff and basalt. Those materials absorbed heat from the hypocaust system and slowly re-radiated it for hours while occupants used the bath. Industrial regenerative heat exchangers followed the same logic. For more than 150 years, blast furnaces and gas turbines have depended on packed beds of dense igneous material because of the exact characteristics that make basalt superior to sand. High thermal conductivity, strong volumetric heat capacity, stability under thermal cycling, chemical inertness. Basalt conducts heat at approximately 1.7 to 2.5 watts per meter Kelvin. Dry sand operates closer to 0.25 to 0.35. That means basalt transfers heat roughly 7 to 8 times faster. During charging, heat penetrates deeper into the basalt mass more rapidly and with greater uniformity. During discharge, each basalt stone maintains surface temperature closer to its core temperature. The result is a flatter and more sustained output curve instead of the steep early drop, followed by a weak, extended tail commonly seen with sand systems. Volumetric heat capacity reveals another major advantage. Basalt at 2,900 kilograms per cubic meter with 850 joules per kilogram per Kelvin stores, approximately 2.5 megajoules per meter per Kelvin. Dry sand stores around 1.34 megajoules. At equal temperature, basalt retains nearly twice the thermal energy within the same volume. Then there is dimensional stability. Basalt resists fracturing and spalling even under repeated thermal cycling approaching 400 degrees Celsius. Quartzite and sandstone gradually crack because their crystalline quartz components expand and contract differently from the surrounding structure. Basalt behaves differently. Its fine crystalline to amorphous structure expands more uniformly and avoids phase transitions within this temperature range. Fill the drum once and the material can last for decades. Lordley described the mathematics behind this in 1887. Then, in 1999, Los Alamos transformed the principle into an operational electricity generator, a thermoacoustic Stirling engine linked to a linear alternator. It produced measurable electrical output without rotating machinery and without combustion. The materials list is simple. Every specification is real. Every listed price can be checked directly at hardware suppliers, landscaping centers, and construction yards in any region with nearby volcanic terrain. The first component is one 55-gallon unlined steel drum, identical to the specification used in the sand battery system. Cost ranges from $8 to $14. It must remain unlined. No plastic coating, no epoxy interior. Bare steel only, capable of tolerating continuous temperatures above 300 degrees Celsius. The second component is basalt rock, weighing between 200 and 220 kilograms. The material should be dense, dark-colored, and fine-grained, broken into pieces, measuring 40 to 80 millimeters in diameter. About the size range between a golf ball and a tennis ball. That sizing creates maximum heat exchange surface while preserving internal gaps for airflow during charging. Avoid large, flat slabs. Do not use material smaller than 25 millimeters. Garden and landscaping suppliers usually charge $4 to $8 for a complete load. Volcanic rock quarries may sell it for $1 to $3. In places without nearby volcanic geology, dense igneous riverstone can replace basalt. Every substitute rock must be tested first. Heat the sample to 300 degrees Celsius using a propane torch, then quench it in cold water 3 times. If no cracking appears after the third cycle, the material is thermally stable. The third item is 1 tube of high-temperature silicone sealant rated for 260 degrees Celsius, the same grade used in the previous builds on this channel. Cost ranges from $4 to $7. The fourth requirement is steel angle iron. 4 sections cut to 18 inches each, combined with 8 M8 bolts, washers, and locking nuts to assemble the support frame. Estimated cost is $4 to $6. The fifth component is ceramic fiber insulation blanket with 25 millimeter thickness, one roll measuring approximately 1 meter by 2 meters. Same specification as the sand battery design. Price ranges between $9 and $14. This insulation wraps around the lower outer section of the drum, directing heat release upward toward the exposed upper surfaces, where the energy becomes useful. The sixth item is a handheld infrared thermometer, a basic model costing $8 to $15. This becomes the primary diagnostic tool for checking charge condition and observing discharge behavior. Total system cost at North American retail prices falls between $52 and $66. In international markets using locally sourced basalt, the total drops to around $18 to $32. In most volcanic regions worldwide, $8 accurately reflects the price of the rock portion alone when basalt is purchased by weight from quarry or garden suppliers. Rock selection is where most first-time builders rush and later regret it. Spend 30 minutes here before loading the drum. Start with the visual inspection. Proper basalt appears dense, heavy, dark gray or black, with fine grain and no visible layering or large crystal structure. It should feel heavier than expected for its size. Porous volcanic material such as pumice or scoria does not work for this system because its thermal behavior differs substantially from dense basalt. If uncertainty remains, perform a water test. Drop the rock into a bucket. Dense basalt sinks immediately. Any stone that floats or slowly descends while releasing bubbles contains too much porosity. Next comes the fracture test. Strike each piece lightly using a metal rod. Solid basalt produces a clear ringing sound. Cracked material creates a dull thud. Discard every dull-sounding piece. Cracks spread under thermal stress and eventually create dangerous sharp fragments. Then perform the thermal cycle test. Select 6 representative stones from the batch. Heat each one with a propane torch until visible, dark red coloration appears, roughly 500 degrees Celsius at the surface. Hold that temperature for 2 minutes. Allow complete air cooling. Repeat the full process 3 times. After the third cycle, inspect every sample carefully for cracking, surface spalling, or audible fracture sounds during cooling. Any failure means the material is thermally unstable. If more than 1 out of 6 pieces fails, obtain rock from another source. If all 6 survive, the entire batch is suitable for use. Wash all stone thoroughly before loading the drum. Landscaping basalt is usually clean, but quarry stone or roadside collected material may contain clay dust, oil contamination, or organic residue that releases gases during initial charging cycles. Continue rinsing until the water runs completely clear. Allow the rock to dry fully. Spread it across a tarp under sunlight for 4 to 6 hours, or oven dry at 100 degrees Celsius for 1 hour. Unlike sand, basalt does not require extreme moisture removal, but all surface water should be gone before the first high-temperature charge. The drum assembly follows nearly the same sequence as the sand battery build, with 2 critical differences: the loading method and the management of internal void space. Inspect the inside of the drum using a flashlight. Remove loose rust flakes using a wire brush. Surface rust does not reduce performance. Loose debris capable of blocking the charge port fitting does. Cut a clean 8-inch diameter opening into the top lid using either a hole saw or a jigsaw. A smooth circular opening produces a stronger silicone collar seal. Install the angle iron support structure next. Build a simple rectangular frame from the 4 steel angle sections using the M8 bolt connections. Size the frame so the drum rests inside the corners while the structure prevents side-to-side movement. A fully loaded basalt drum reaches a total mass between 320 and 340 kilograms. That is heavier than a sand-filled drum of identical size because basalt carries much greater density per unit volume. The support frame must be built solid and checked for level before any loading begins. Once the system is filled and placed, moving it becomes unrealistic. The weight alone makes relocation impractical. Loading basalt works differently from loading sand. The rock forms a packed aggregate bed with a natural void fraction between 35 and 40%. Those empty spaces are not defects. They are essential to the design. The trapped air becomes part of the thermal mass, while also acting as the medium that allows charging heat to convect downward through the full depth of the rock bed. Do not pack those gaps with fine material. Place the basalt carefully during loading. Never drop stones from height. Impact damages the drum interior and can fracture the rock itself. Lower each bucket or shovel load slowly, allowing the pieces to settle naturally into position. After every 200 millimeters of depth, shake the drum gently from side to side by pushing alternately against opposite walls. This helps the stones settle into a tighter and more stable arrangement without mechanical tamping. Continue until the rock surface sits within 80 millimeters of the drum rim. Because basalt transfers heat faster, the exterior drum wall operates at higher temperatures during discharge. To direct that heat into useful output, wrap the ceramic fiber blanket from the base upward to 100 millimeters below the lid rim. Leave the upper 100 millimeter band in the top lid uncovered. That exposed area becomes the primary heat output surface. Since basalt moves heat rapidly and evenly into the drum wall, the upper zone maintains noticeably higher temperatures than an equivalent sand battery at the same charge condition. Infrared thermometer readings commonly show temperatures 15 to 25 degrees Celsius hotter. Secure the insulation blanket using steel tie wire every 150 millimeters vertically. Tighten firmly, but do not compress the blanket. The insulating performance depends on maintaining loft. Apply a continuous bead of high-temperature silicone along both the upper and lower blanket edges, where they contact the drum. This creates a seal that stops airflow from bypassing the insulation around the edges. Cut a ceramic fiber disc for the bottom of the drum and secure it with tie wire. Base insulation matters even more with basalt than with sand because basalt aggressively pulls heat toward the lower drum surface. Without insulation underneath, roughly 15 to 20% of stored energy disappears into the floor. With insulation installed, that energy exits through the top, where it becomes usable. Install the charge port collar into the lid opening using high-temperature silicone. Apply a full bead both above and below the collar ring around the lid surface. Allow 4 hours for curing before introducing heat. Charging follows the same procedure used with the sand battery. A rocket stove, enclosed firebox, or solar thermal collector connects directly to the charge port. The basalt system reaches full charge faster because heat moves through dense stone more efficiently than through sand. Anyone switching from a sand battery will notice higher surface temperatures during the first cycles. The basalt is not overheating. It is simply storing more energy from the same heat input. For the first 3 charging cycles, reduce charging duration by 20% compared to the normal sand battery routine. After the 3rd cycle, measure the maximum surface temperature at the top drum face. If the reading remains below 200 degrees Celsius, increase the next charging duration by 15%. If the reading exceeds 280 degrees Celsius, reduce charging time by 15%. Continue adjusting until peak surface temperature stabilizes between 220 and 250 degrees Celsius. That becomes the calibrated full charge condition. The charge port should include a damper, a simple adjustable steel plate that slides over the opening and can move between fully open and fully closed positions. During charging, keep the damper completely open to allow unrestricted airflow through the rock bed. The moment charging finishes, close the damper entirely. Closing the port reduces convective heat loss by preventing warm air circulation through the opening during discharge. That single action extends usable discharge duration by approximately 8 to 12%. No additional material cost, no complicated mechanism. 3 seconds of work. Take 4 infrared temperature readings at the upper drum face after every charge cycle, and again at 2-hour intervals during discharge. Measure north, south, east, and west positions. A properly packed and evenly charged rock bed produces readings within 15 degrees of one another. Differences greater than 40 degrees indicate uneven charging. If that occurs, repack the upper stone layer or clear any obstruction near the charge port. The comparison numbers are direct. Same drum size, same charging source, same duration, same insulation, same ambient conditions. A sand battery typically reaches surface temperatures between 160 and 190 degrees Celsius after a 2-hour charge cycle. A basalt battery under the same conditions reaches between 195 and 235 degrees Celsius. 6 hours after charging, a sand battery surface usually falls to between 95 and 115 degrees Celsius. A basalt battery at the same 6-hour mark maintains significantly higher retained heat. The difference is not theoretical, it is measurable. It comes directly from the material itself. If you want more engineering breakdowns, thermal storage systems, and low technology energy infrastructure explained step by step, stay connected for the next build. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.